All right, in this video, we studied Euclidean spaces. A Euclidean space is a set of tuples of real numbers equipped with the distance function. So the easiest example is the set of real numbers. So this can be made to be a Euclidean space if we define a distance between any 2 points in this set. Any element of this set can be visualized as a point on the number line, right? So we can define the distance between any 2 points, any pair of points in this number line as the absolute value of the difference between these two numbers. Okay, for example, if we have x and y here, the distance between these 2 points can be defined as the absolute value of the difference between these 2 points. So this is the distance between these 2 points. And in case of two-dimensional space, so this is actually the Cartesian product between two sets of real numbers, which is defined as ordered pairs of real numbers, where x and y are both real numbers. Okay, any elements of this set can be visualized as a point on a plane. So any point here, x and y, can be visualized as a point. And if there are 2 points, we can define the distance between these 2 points. So how do we define the distance? That is this, right? Okay, so let's say this is x1, y1, and this is x2, y2. Okay, the distance between these 2 points is defined as the square root of x1 minus x2 squared plus y1 minus y2 squared. So this is the distance. So according to the Pythagorean theorem, right? So this difference here corresponds to this. And this distance difference here between y coordinates corresponds to this. Okay, so according to the Pythagorean theorem, this length is the square root of x1 minus x2 squared plus y1 minus y2 squared. And similarly, we can define the three-dimensional Euclidean space as this. This is a triple of real numbers. So x, y, z, and x, y, z are real numbers. Okay, so any element of this set can be visualized as a point in three-dimensional space, like this. So any point. And we can define, of course, distance between 2 points. And that, let's say we have x1, y1, z1, x2, y2, z2. And the distance could be defined as this, x1 minus x2 squared, y1 minus y2 squared, and z1 minus z2 squared. Right? So this is the distance between these 2 points. And we can continue this process to any numbers like R4, that's 4-dimensional space, and 5-dimensional space, and we in general we can write r to the power of n. So this is n-dimensional space. So r to the power of n is a tuple of n real numbers. Okay, so there are n r's here, which is defined as, we write, since we ran out of symbols, we write x1, x2, and so on up to xn, where all x1, x2, and so on are real numbers. But for general n, we cannot visualize these elements as a spatial object, but we still follow the same intuition as 2 or 3-dimensional spaces, so that the distance between 2 points in this space, so let's say we have x, where there are n real numbers, x1 to xn, and y. So these are 2 points in this n-dimensional space. And the distance between these 2 points is defined as this: x1 minus y1 squared plus x2 minus y2 squared, and so on, and xn minus yn squared. So everything's, these differences squared are summed, and we take the square root. So that's the distance between these 2 points in this n-dimensional space. In general, this space, r to the power of n, and the distance function. So distance function is a function of 2 variables actually. So 2 variables. So this pair, so this set and the distance function, is called the Euclidean space. And this distance function is called Euclidean distance. Next, I explain an important inequality, a famous inequality called the Koshi-Schwartz inequality. Schwartz inequality. Maybe you have learned this in linear algebra, but anyway, let's explain this. Suppose we have 2 points in n-dimensional space, Euclidean space, a1, a2, up to an, and b, b1, b2, up to bn. Then we have the following inequality. That is, if we take the sum from 1 to n, ai, bi, absolute value, this quantity is less than or equal to this: ai squared and square root of bi squared. So this inequality is called the Koshi-Schwartz inequality. Basically, if you know some linear algebra, this is the dot product between these 2 vectors, and these are the length or the distance from the origin of these 2 points. So let's prove this. And to prove, the proof is actually quite easy. So first, if this A is the origin, then this inequality is trivial because the left-hand side is 0, because all of AI's are 0 here. And then this part, so the length of this, the distance between A and the origin is 0 because A is the origin. So both sides are 0, so therefore this equality holds. Therefore this inequality, including the equality, is true. So if A is 0, then the equality holds. Actually, it is an equality, but anyway, this is true. So now suppose A is not the origin. Okay, so for any real number t, we have the following. Okay, the sum from I equal to 1 to n of ai t plus bi squared. Now this is always greater than or equal to 0 because ai and bi, they are all real numbers and t is also a real number. So this holds. Now the left hand side, if we expand this, is equal to sum of ai squared t squared and 2ai bi t plus bi squared. So let's consider this as a quadratic form of t. So let's summarize this. Take this t squared out. We have I from 1 to n ai squared t squared and 2 I from 1 to n ai bi times t plus bi squared. Okay, so this is a quadratic form of t. So what this means is that the discriminant, so this means this is always greater than or equal to 0. So what this means is that the discriminant of this quadratic form is negative or non-positive. So that means this squared minus this ai squared times this is less than or equal to 0. So graphically, if we plot this as a function of t, it should look like this. It is always above this horizontal axis, or maybe it can touch this horizontal axis, but it can never go below this. So this never happens. Okay, so that's what this means. Okay, now if we move this part to the right, we have ai bi everything squared is less than or equal to this ai squared times bi squared. And if we take the square root of both sides, positive square roots, then we have the desired result. And we're done. And if we happen to know something about scalar product or dot product of vectors, then this left-hand side is this dot product, right? ai bi sum of this. So this is the dot product. That is a1 b1 a2 b2 and so on. And the right-hand side is this, the length of the vector. So that is a1 squared, a2 squared, and so on. And same for b. So the Koshi-Schwartz inequality indicates that the absolute value of the scalar product between two vectors is less than or equal to the product of the length of two vectors, of these two vectors. It's the same thing. Next, we prove some important properties of the distance function in general, okay, which is called distance axioms. Although this is not an axiom at all in this case, but it's a theorem. Suppose we have this n-dimensional space and the distance function. Okay. Then the distance function satisfies the following three properties. Okay. First is non-negativity. Okay. For any x and y that are elements of this n-dimensional space, we have the distance between these 2 points is always greater than or equal to 0. And in particular, if the distance between 2 points is 0, that means that is possible only if and only if x is equal to y. Okay, so the distance between 2 points can be 0 only if and only if these 2 points are actually the identical point. Okay, so that's the first property. And the second property is the symmetry. For any x and y, we have d of xy is equal to d of yx. This is trivial, I think. The first one is also trivial. And the third one is not so trivial. For any 3 points, x, y, z, we have distance between x and z is less than or equal to the sum of the distances. The distance between x and y and the distance between y and z. Okay, now let's prove this. The first two are actually trivial because of, let's look at the definition of the distance again. Let's say we have x, x1, x2, and xn, and y, y1, y2, yn. Okay, so the definition of the distance between these 2 points was this: x1, y1 squared, x2 minus y2 squared, and xn minus yn squared. Because of this functional form, this is of course non-negative, right? This is a positive root, square root. So it is non-negative. And if this is 0, so suppose the distance is 0, then that means all of these are 0, right? So this means x1 minus, let's say xi minus yi squared is 0 for each of I, 1, 2, up to n. So this means xi is equal to yi, right? So this means for of course all of this, right? So this means x is equal to y. Okay. And on the other hand, if x is equal to y, then we have this, right? So we can go backwards. And if each of xi and yi are the same, then of course the difference is 0. So therefore this holds. So if all of these are 0, then the distance is 0. So the distance between 2 points is 0 if and only if these 2 points are the same point. And we're done for the first part. And the second part, symmetry. Okay, symmetry. So this was the definition. Okay, but of course, x1 minus y1 squared is equal to y1 minus x1 squared. So xi minus yi squared is equal to yi minus xi squared. So if we do this, then it's clear that this is equal to d of yx. So if we swap the order of x and y, and we still get the same quantity. Therefore, the distance function is symmetric. And now let's prove the third part. And this is not trivial, but it can be made a little bit simpler. So let's say we have x is this and y is this and z is this. Okay, and so if the, okay, so this inequality is called triangle inequality. Okay, suppose if this holds, then we should have, so if this triangle inequality holds, we have this. And yz. Okay, so apply the definition of the distance function. We should have this. And this. yi squared Okay, to simplify the notation, let's put this as okay, this part as ai and this part as bi. Okay, so that means ai is equal to xi minus yi and bi is yi minus zi. Okay, then xi minus zi is xi minus yi plus yi minus zi. So we add yi and subtract yi, so they're the same thing. But this part is ai and this part is bi. Okay, so this triangle inequality can be also written as this. Sum of ai plus bi squared and the sum of ai squared plus sum of bi squared. Okay, and so suppose this holds. Okay, if we square both sides, so square both sides, we have this part becomes just this ai plus bi squared, and this part becomes this sum squared, sum of squares, and plus 2 square root of ai squared and square root of sum of bi squared and plus sum of bi squared. Okay, and if we expand this left hand side, we have ai squared plus 2ai bi plus bi squared, but we can split this summation into ai squared plus 2 ai times bi plus sum of bi squared. Okay, now compare the right hand side and the left hand side. We have this same term here, ai squared, sum of ai squared, and sum of bi squared, so they can be cancelled, and this 2 can be cancelled. So we have what's left is ai bi, sum of ai bi, less than or equal to this square root of sum of ai squared times square root of sum of n bi squared. But this is true for any points ai bi. So this is Koshi-Schwartz inequality. Koshi-Schwartz. Okay, so this is true. So if we trace this argument backwards, so since this is true, of course, the original Koshi-Schwartz contained absolute value here, but we can just get rid of this absolute value, and this is still true, right? So this is just between less than or equal to this this quantity and greater than or equal to negative of this quantity. So this inequality is still true according to the Cauchy-Schwarz inequality. So we trace backwards this argument. So from here, we add these terms to both sides. So we have this inequality. And then take the square root of both sides, and we have this inequality. And therefore, we have this triangle inequality. Okay, so we are done. But why is this called triangle inequality? So in any space, if we have 2 points, x, y, and z, okay. So this inequality shows that this length is always less than or equal to the sum of this length xy and yz. Okay, so this inequality holds for any triangle. So that's why it's called triangle inequality. In this theorem, we have proved these properties for the Euclidean distance. So this particular distance function. Okay, but we can reverse this argument so that any function, so let's forget about the Euclidean distance. So let's say this d is a function of 2 variables. Those variables are elements of this set, r to the power of n, n-dimensional space. If this function d satisfies these 3 properties, conditions, then we call it a distance function. Okay, and Euclidean distance is just one of these possible functions. Okay, there are other possible distance functions. For example, instead of summing the difference, squared difference, sum of squared differences, we could define the distance function as sum of absolute value of differences. Then it is still a distance function. For example, if we say x and y are elements of this, and we can define, let's say, d1. This is a function defined by this. Instead of square root of sum of squared differences, we just take the sum of absolute value of differences. Okay, so this is x1 minus y1 plus x2 minus minus y2 plus and so on. This is also a distance function. Okay, but it's a different kind of distance function. And you can prove that the function defined by this also satisfies these three conditions: non-negativity, symmetry, and the triangle inequality. You should try that. And there are many kinds of other distance functions. And finally, we define an important notion of the epsilon neighbor that will be useful for later studies. Let's define it. Epsilon neighbor. Epsilon is actually any positive real number. Epsilon neighbor. For any, let's say x is a point in this n-dimensional Euclidean space, and epsilon is any positive real number, okay? Then the epsilon neighbor of the point x is, we write like this, n epsilon x. This is a set defined by this. So this is a subset of this n-dimensional space such that the distance between x and a point in this subset, any point in this subset, is less than, strictly less than epsilon. Okay? So this is called epsilon neighbor. And this symbol epsilon is just arbitrary, okay? So we could use delta, or we could use A or alpha or whatever, or 1. So what this means is that it's a kind of interior of sphere or hypersphere. So let's say this is x, and epsilon neighbor is something like this. So it's all these points inside this circle or sphere of radius of epsilon. Okay, so all these points are elements of this epsilon neighbor of x. Okay, let's see some examples. In the case of one-dimensional space, epsilon neighbor is this. It's an interval between x minus epsilon and x plus epsilon. Okay, so if we draw the number line, if this is x, then epsilon neighbor is an open interval. So this point is x minus epsilon, and this point is x plus epsilon. So the distance between these endpoints and x is epsilon. Okay. And in case of two-dimensional space, let's say x is somewhere here, then its epsilon neighbor is the interior of the circle of radius of epsilon and centered at x. So this inside this circle is the epsilon neighbor. And in the case of three-dimensional space, it's interior of a sphere centered at x and with the radius of epsilon. Okay, that's it. That's all for today.